make sure this is running. Okay. Okay, so this is chemistry. The course itself revolves around the study of chemical reactions. But before we get deep into the study of chemical reactions, I'm going to review basically the protocol and the evolution of chemistry studies up to this point. So the first few comments will talk to you about how Chem 1 evolved and why you are where you are right now. Then we'll get into how Chem 2 builds on Chem 1. As you entered the intermediate levels in chemistry, or whatever level in chemistry, what you did is you are looking at a study of matter. And matter is anything having weight and occupies space. So that really embodies more than we can chew and swallow at one time. It's overwhelming at the number of things that have weight and occupy space. So the scientists must condense all this down into a simpler form. And that simpler form is called the atomic theory. It's the basis from which we study chemistry. Now, the first atomic theory, just as a trivia, Democritus in 600 BC stated that if you take a piece of matter and split it in half, and then take one of those and split that in half, and one of those and split that in half, and so forth, you would eventually come to an indivisible particle. The Greek word for indivisible particle is atomos. From which we, of course, get the word atom. Now, that was based exclusively on a philosophical point of view. But to be modern and more practical, we need to base the concept or the atomic theory on a experimental foundation. Dalton's atomic theory is the basis for the study of general chemistry across the world for 99% of courses that are taught. It has a set of postulates, you may remember, whereby he indicates that all matter is made up of particles. That's the first thing. Particles interact by opposites attract forces. All particles which have the same structure are the same, and all particles which are different structures are different. And they have arrangement based on their structure. And they call it the periodic table, or elements. And elements interact with other elements, or compounds, to produce chemical reactions. And there are only three things you can get out of a chemical reaction anyway: a solid, liquid, or gas. And there are billions of each one, but you can only get one of three. Now, we're not talking plasmas in the high temperature range. We're talking about basic concepts of things that are solid, liquid, or gas. And then if you mix a solid against a gas or liquid into a liquid or solid and liquid, you're talking solutions. So what that looks like is you go through your basic course in chemistry. So Chem 1, well, he didn't know what fundamental particles were at the time. We do know now the fundamental particles are the subatomic structures. So we're going to say from protons, electrons, and neutrons. Now, this was not part of the original Dalton theory. The original Dalton theory just said an atom of carbon were black circles and stuff like that. He didn't have a C12 and all that. But we know now, and so we include the fundamental particles, protons, electrons, neutrons. And what do those do? Those make atoms. And it is very important that you understand the word atom refers to a single element. There's atoms of hydrogen, atoms of helium. But when we translate that into the word elements, we're talking about a whole lot of atoms of a general type. So it's a matter of semantics here. So an atom is a nucleus with protons and neutrons and then surrounded by electrons. And that could be any one of the 100 and some odd elements on the periodic table, as you already know. If we take a lot of hydrogen or a lot of carbon, then we say, well, that's a quantity of elements. Elements interact with elements to produce molecules. And in the same context, a molecule is an individual structure. But from molecules, we talk about compounds. The same thing, but the difference is compounds are a whole lot of molecules in the context of what we're studying. And there's a lot of chemistry that goes in there, and you know. Now, compounds interact with compounds and or elements through chemical reactions. Right there. And there was a section in your general chemistry course where you learned about how to balance equations, how to write the yield of equations, how to apply stoichiometry to various equations. And they give you moles, and they give you mass, and they give you particles, and you mix all that up, and you come out with a practical number that means something. Well, that's in your chemical reactions. Now, as I said 2 or 3 minutes ago, from chemical reactions, you have states of matter. Solids, liquids, and gases. Millions of them exist, but that's all that's produced, a solid, a liquid, and a gas. If you get hot enough, all of the neutrons, protons, electrons come apart, and so forth and so on. We're not working in that. And then if you mix the solid into a liquid like salt and water, you get a solution. So from the last issue here, we get solutions. The last chapter in Chem 1 that we cover, if y'all have had me before remember, was solutions. And this is why it's placed in that position, because it is the more complex issue relative to the study of matter. We talk about matter, how it breaks down into the different categories, how molecules are broken down in different categories and so forth like that in Chem 1. But then we leave this and we come back to a study of chemical reactions. Now we enter Chem 2. In your case, Chem 1412. A study of chemical reactions. So the point in this initial comment is to show you where you are. Now, of course, you know there's tons and tons of information packed in this little schematic here. And it's very important that you go back and review if you need help with it. And I will answer questions even in Chem 1 stuff. If you're struggling with a Chem 1 problem that you found, you need some help with it, you send me what you've done, I'll help you with that too. I mean, this doesn't exclude those. This is a chemistry course. As far as I'm concerned, it's all science. At any rate, how do you study chemical reactions? Okay? That's what I'm here to teach you. There are 3 ways to study chemical reactions. 1, 2, 3. Okay? The first one we're going to look at is chemical kinetics. Chemical kinetics deals with the rate, speed, how fast of a reaction. Starting with 0 products, 100% reactants. We're going to make products. How fast do you make them? Well, that's what this topic deals with. How fast do we make the products we're interested in? Once those products are made, you enter into what we call a steady state condition, and that's chemical equilibrium. I'll show you how all this ties together in just a minute. Chemical equilibrium is the study of extent of reaction. E-X-T-E-N-T of a chemical reaction. And finally, and I'll explain all these in detail as we go, and finally, there's chemical thermodynamics. Which deals primarily with the feasibility of a process. You apply the principles in thermodynamics to the reaction you're working on, it says it will work or it won't. That's what thermodynamics is all about. Thermodynamics is a reasonably young component of study of reactions, and it evolved out of the need to evaluate steam engines and heat transfer processes during the Industrial Revolution. So it is a very young science in terms of what we're going to do. But to master this, from where you are at this point in your study of chemistry, we need to start with the idea of chemical kinetics. Now I want to show you how all 3 of these tie together and why they are incorporated in the context of the Chem 2, study of chemical reactions. And the way we're going to do this, we're going to take a reactant, general reaction. Well, what's on the left side? Well, reactants, and what's in the middle? Yields products. So we're going to start out with a chemical reaction, start out with reactants, and the outcome of this are products. Okay, so mark down a little graph axis on the vertical axis where you want to look at the idea of concentration of reactants or products in some cases. And on the horizontal axis over a function of time. Now if you were talking about how fast are you driving your car, how do you respond? In miles per hour. That's a rate. That's a speed. Well, in chemistry we respond in terms of concentration changes as a function of time. Instead of miles per hour, we say moles per second. Moles per liter second. And you'll see how this went. How does concentration change? Molarity is a concentration number. Molarity per second. So, in the analysis of the kinetics and speed of a chemical reaction, we need to start at, of course, time 0. Now listen to me carefully. This is a very important little footnote here. We're going to treat the chemical reaction as a horse race. All the reactants in our reaction are in the starting gate. And it has not, the bell hasn't gone off and the horses aren't running yet. But we got them in the starting gate. How much product do you have at that point? None. Yes? You haven't got any product. It haven't started yet. You haven't opened the gates. The horses are still in the gate. So the reactants are 100% at this point. And the products are 0% products. Okay, open the gates. What's going to happen? Are we going to start making products? Somebody nod. Okay. And over time, it will follow a trend that will look like this. The reactant concentration will drop off to that point, and the product concentrations will increase to, say, a point like this. And at some point in the course of this process, it will appear, listen to me, it will appear that the product concentration and the reactant concentrations stop changing. So if we took a ruler and extrapolated back here to the best of our ability, from this point on, let's just say it levels off there. From this point on, where I've drawn the vertical lines, concentrations don't change. Now, the concentrations are actually changing, but the rate of the forward reaction equals a rate of reaction in reverse. Over here to the left of this curve, vertical line, you never have a zero slope of any tangent line that you put on there. You start here, draw a line, see there? It touches. That's not zero. Vertical is 1, and then it begins to decrease to horizontal, which is 0. And so if we took another point, say right there, and drew a tangent line, that's still changing. And if we did another line right in here, it's still changing. Not until we get into this region do we have zero slope. And that's the marker that says you have now entered the equilibrium zone. Sounds like something out of Twilight Zone there. Okay, equilibrium. From that point on the left side is the kinetics. The things that are going on in the study of that chemical reaction, as we study the rates of reaction, will be occurring in this portion of that graph. Thermodynamics takes both the kinetic end and the equilibrium end and applies those concepts to come up with what we call a free energy concept, which we will explain in great detail when we get there. If the free energy number, when you put all the numbers in, comes out negative, then the reaction is said to be spontaneous, or will go without you doing anything. It's like an electric battery. Those are spontaneous. Or if you apply it and you come out with a positive free energy, and it says it's not spontaneous, you've got to push it uphill to make it run. Okay? So when we get to thermodynamics, we'll present that in the appropriate format, and it will hopefully, you can see how equilibrium concepts are applied to define the feasibility in the thermodynamic region in here also. Our interest at this particular point in your study is the study of kinetics. So let's talk about chemical kinetics. As indicated in the introduction, chemical kinetics is a study of rates of reaction from beginning to the point in which it enters the equilibrium condition. From initiation, or where it starts, to beginning of equilibrium. Hopefully that makes sense after drawing out a little representative illustration for it. How do we study chemical reactions? What do we look at to determine what the speed of a reaction is? Okay? We call them rate factors. The study of reaction rates are proportional to rate factors. What's a rate factor? Don't write all this. These are items. When you change them, change the concentration. Remember the concentration time graph. If you change the concentration, you will change the rate of reaction. There are 5 rate factors. And they're real easy to remember. You will remember this for the rest of your life. The acronym will spell the rate factors. C, A, N, T, C. Can't see. This is an acronym for those 5 items. If you change something, you change the rate of reaction. So you say, okay, I change concentration. What does the reaction do? Oh, it changes the rate. Or if it doesn't, you call it something else. You call it a zero order reaction. If you change, that would be C here. Let me go ahead and list them all so you'll understand the idea. Concentration factors. You change concentration, change rate of reaction. It depends on the chemistry of the reaction and the nature of it. Area. In other words, this is surface actually, surface area. This is pretty easy to understand. If you want to start a campfire, what would you use? You'd use kindling, some small wadded up papers and stuff instead of a big log and then try to stick a match under it. Well, what you're doing is increasing the surface area for which the reaction can take place. The greater the surface area, the faster the reaction. That's fundamental. Okay? Nature. You can change a molecule in a very slight way and you'll change the rate of how a reaction takes place. You're going to, y'all will actually do this. You're going to look at the savolyses of T-butyl halides. What? Okay. Don't write this. This is just a, well, yeah, if you wish. These are T-butyl halides. What's a halide group? Group 7, wasn't it? Remember that? Fluorine, chlorine, bromine, iodine. Acetine's not usually into it. Look at these. Everything in this structure is the same except the halide. If I put this in water, or this one in water, the outcome here and here will be a T-butyl alcohol and HCl. And this one will give you T-butyl alcohol and hydrobromic acid. The thing to get from reactants right here, two products, are two different rates. The speed at which T-butyl chloride reaches this point and the speed at which T-butyl bromide reaches the point with products are different. The speed is different. Why? Because nature is changing that molecule. Now that's a simple example of billions of small changes in a molecule that you can make and change the whole picture of how things are produced, speed-wise and so forth. Temperature. This is easy to understand. Why do you cook your food? So it will react and you'll get all the nourishments out of it. You don't eat raw food. Well, the purpose of cooking it is to accelerate the reactions that will make it nutritious. Okay? Typically, if you heat an organic reaction, it typically will go faster. If you heat an inorganic reaction, typically it will either do nothing or slow down. But this is the factor that if you change temperature, something happens to the rate of reaction. And it depends exclusively on the nature and character of that reaction. And finally, catalyst. Catalysts are independent chemicals that, when added to a reaction process, affect, A-F-F-E-C-T, affect the rate of reaction. There are two kinds of catalysts: accelerators and retarding agents. But they both affect the rate of reaction. There are times when you want something to cook faster or reach products faster, so you throw in a catalyst. Millions of catalysts out there. Or you might put in something that will slow the reaction down. When you put antifreeze into your radiator of your car, it contains a number of retarding agents so that corrosion will be reduced. It's a catalyst. However, the catalyst in itself is not consumed by the reaction. It just functions to affect that reaction and the outcome of that reaction. So now what do we learn? You are now at a point in your study of chemistry at which you can look at a more sophisticated level of study of chemical process. And that is the study of chemical reactions. How do we study chemical reactions? We have to understand that there are three primary ways. When you study chemical reactions, you're not limited to just concentration studies. You can study all of these, but you can only study one at a time. You change concentration, see what happens. Or you change area and see what happens. Or you change the molecule like we did down here. Well, I'll study the rate and come up with a rate law for this one, and then I'll come up with a rate for this one. And say, oh, the numbers are different, so that means the rate's different. Now you're going to do that, and I'll show you how to do it. We'll walk through you, and you'll see how. Or you find a catalyst that will speed the reaction or slow the reaction, and you look at the rates at which they occur. Now, as we begin the next time you come in here, so our first topic in kinetics is rate as a function of concentration. And what are we doing? Concentration. What does that mean? You put more in or less, right? I'm going to increase systematically the amount of reactant and see how the reaction changes. We're going to develop an experimental process around this and see how we get raw data and translate it into the idea of rate and rate reactions. When you write a rate as a function of a concentration, you are generating a rate law. So rate as a function of concentration, or rate as a function of a rate factor, whatever comes out with a mathematical equation, and that is a rate law. Make it plural, rate law. Under the concept of rate proportional to a concentration, you are going to look at 4 rate law concepts. You're going to look at rate averaging. Very easy. Rate final minus rate initial over the time you were looking at it. Rate is a concentration change as a function of time, called rate averaging. Rate proportional to a function of reaction coefficients. H2H2 plus O2 gives you 2H2O. Well, the number before hydrogen is 2. The number in front of oxygen is 1. That the one with the bigger number is doing its thing faster than the one with the smaller number. That's what it means. But you got to balance the equation. This only applies in balanced equations. So the bigger number means it's going faster. But we can put numbers to it. I'll show you how. Rate as a function of experimental observation, or we call these experimental rate laws. So you start off with a reference concentration, 0.1 molar compound. And you measure the rate of reaction for 0.1 molar compound. Then you double that concentration. You're going to see how fast it goes, if it goes faster, by going to 0.2 molar compound. You measure the compound. You compare the two. Okay? One doubles, you double concentration, double rate. What if we double it and goes up 4 times? What if we double it and doesn't do anything? Those are experimental rate laws. And the only way you can write the experimental rate law is by observation and writing data down. That's the study solvolysis of T-butyl halides that we're going to do. It's going to be an experimental rate law. Take a look at it when you want to read the paper. It's in there. You got a lot to work on. And 4, decay process. When a reaction proceeds from reactants to products, the concentration of reactants decreases, right? We saw that earlier in our little graph. We started out with 100% reactants, and over time it did this. Okay? What if you take a second reaction and you run it, and it does this? It starts out here and drops down real fast like that. Or if you look at a third reaction, and it kind of goes sluggish like that. Those have different rates, and they're classified in terms of a decay process, and we call those orders of reaction. This might be a second. The faster the rate, faster the drop, the higher the number. So second order. This one would be, say, a first order, and this one may be a 1 point. They can go in fractions, a 0.5 order. Now we'll keep whole numbers in the problems we do, but they can have. And if you have one that lines up like that, it's called a 0 order. Oh, this is incorrect. Sorry. This should be rate versus concentration. So, my bad. Senior moment. So if you want to see how the rate changes as a function of concentration, this is what you're doing. You'll have a concentration number 1, you see what the rate does. Concentration number 2, see what the rate does. Concentration number 3, see what the rate does. That's the idea behind the decay process. Reactants are going away. All radioactive process, if anybody doesn't know this, is first order. All radioactive. But chemical reactions have a variety of orders of reaction. And we're going to build on this next time. You come here, and like I say, I'm not going to give you a quiz next time. But after this, you can expect quiz. Oh.